Welcome everyone to section 7.2, more on eigenvalues. Okay, so in section 7.1, we defined what an eigenvalue and an eigenvector was and how you would take the determinant of A minus lambda I to compute all the eigenvalues and find the null space of the matrix A minus lambda I to find their corresponding eigenvectors. Okay, now we're going to be looking at the multiplicity of eigenvalues. Okay, so things to keep in mind when we go through this section. Okay, when do the eigenvectors of a matrix A form a basis for Rn? And what relationship does the multiplicity of the eigenvalue and the characteristic polynomial share with the number of linearly independent eigenvectors associated with that same eigenvalue? Okay, so we'll look at two examples. Okay, both 3 by 3 matrices. Okay, they'll be similar in some ways, different in others. Okay, find all eigenvalues and eigenvectors. Okay, so first off, we need to look at the matrix A minus lambda I. So it's 3 minus lambda, minus 1 minus lambda, and 2 minus lambda. Along the diagonal, nothing else changes on the off diagonal. Okay. Because we're taking the determinant of this matrix, we can expand across any row or column. Okay, I will do the first column because there's more zeros in it. So I get a positive 3 minus lambda times the determinant of minus 1 minus lambda, minus 1, minus 4, and 2 minus lambda. Minus 0 times, well, it doesn't matter. Plus 0 times, well, it doesn't matter. Okay, so that's the whole idea, taking the determinant down the first column. The other 2 by 2 determinants don't matter. So this is the characteristic polynomial. And so what do we get that to be? We'll call it P of lambda. 3 minus lambda times minus 1 minus lambda, minus 1 minus lambda times 2 minus lambda, minus 4. And we're going to set that equal to 0. So we get 3 minus lambda times negative lambda is lambda squared. We get plus 2 lambda minus 2 lambda. Sorry, plus lambda minus 2 lambda. So that's a minus lambda. Negative 1 times 2 is a negative 2. And that's minus 4. Let me make sure I did that right because it doesn't feel right. Minus lambda times minus lambda is lambda squared. That's plus lambda. That is minus 2 lambda. So that's minus lambda, and negative 2, negative 1 and 2 makes negative 2. Okay, that looks good so far. So I get lambda squared minus lambda minus 6. There we go. So we get 3 minus lambda times lambda minus 3 times lambda plus 2 equals 0. And so what are our potential eigenvalues? We get lambda equals 3 and lambda equals negative 2. Okay, so there's lambda equals 3, there's lambda equals 3, there's lambda equals negative 2. All right, so now we find the corresponding eigenvectors. So let's look at lambda equals negative 2, and we'll look at lambda equals 3. So for lambda equals negative 2, okay, we substitute in negative 2 for lambda, and we get the matrix 3 minus negative 2, that looks like it's 5, minus 4, minus 1, 0. Negative 1 minus a negative 2, that looks like it's 1, negative 1, and we get 0, negative 4, and 2 minus the negative 2, that's positive 4. So we row reduce this, we get this to be 5, negative 4, negative 1, 0, 1, negative 1, and this is 0. Well, if I scale this by a divide by negative 1, negative 4, we get this to be 0, 1, negative 1, so that's 0, 0, 0. So we have a pivot, or what would be a pivot in this column, what would be a pivot in this column. That column is free, so x3 is free, x2 is equal to x3, and we get the equation 5x1 equals 4x2 plus x3. Now, taking this equation right here, 5x1 is 4x2 plus x3, that's the same as 4x3 plus x3, because after all, x2 is equal to x3. So 5x1 equals 5x3, so we get x1 is equal to x3. So the null space consists of all vectors x1, x2, x3 that look like x1 is x3, x2 is x3, and x3 is x3. So they're all scalar multiples of the vector 1, 1, 1. Now looking at lambda equals 3, what do we see here? So I'm going to write in red. No, I'll write in purple. Next to lambda equals negative 2, the corresponding eigenvector is 1, 1, 1. What about for lambda equals 3? Okay, so we go up to our original matrix, we plug in 3, and we get 3 minus 3, that's 0. Minus 4, minus 1, 0. Minus 1, minus 3, so that's minus 4, minus 1. 0, minus 4, 2 minus 3 is minus 1. All right. So what does this row reduce to? 0, 4, 1, 0, 0, 0, 0, 0, 0. So there is a pivot in this column, okay? This is free and this is free. So x1 is anything it pleases. 4x2 is equal to negative x3, and x3 is anything it pleases. So what does this reduce to? Okay, we have x1, x2, and x3 is equal to x1 minus 1/4 x3 and x3 and so that now becomes x1 times 1, 0, 0 plus x3 times 0, negative 1/4, and 1. So you see there's two different vectors that span the null space of A minus lambda I, where lambda I is, that corresponds to lambda equals 3. So there's two linearly independent vectors. I know they're linearly independent because they're not scalar multiples of one another, that span the null space for A minus lambda I. So I'm writing this in purple. The vectors are 1, 0, 0, and I'll clear the fraction right here. 0, -1, and 4. Again, I'm just multiplying this vector by 4 so that I don't have -1/4 in the middle term. Now you see something's a little bit different here. Lambda equals 3 has two linearly independent eigenvectors that span its null space. Lambda equals -2 only has the 1. Now, it doesn't seem like a coincidence that for lambda equals 3, there was two factors of it in the characteristic polynomial. With lambda equals -2, there was only 1. So that's interesting. Keep that in mind as we go to the next example. Now we'll do the same thing for this matrix. 4, 1, 6, -4, 0, -7, 0, 0, -3. So we look at A minus lambda I. So the determinant, so A minus lambda I looks like what? It looks like 4 minus lambda, 1, 6, -4, 0 minus lambda, -7, 0, 0, -3 minus lambda. Okay, and this time we'll expand across this row. Okay, so the coefficients are going to be minus, plus, minus. So the determinant of A minus lambda I is going to be equal to positive 0 times doesn't matter, -0 times it doesn't matter, positive -3 minus lambda times the determinant of the 2 by 2 matrix, 4 minus lambda, 1 minus 4, and minus lambda. So we do this, -3 minus lambda times, so 4 minus lambda times negative lambda. This is all going to be multiplied by -3 minus lambda. It's minus a -4, minus a -4. So that's -3 minus lambda times lambda squared minus 4 lambda plus 4. So that's equal to -3 minus lambda times lambda minus 2 squared. So you see here, when you set this equal to 0 and solve, you get lambda equals 2 as an eigenvalue and lambda equals -3. So let's take a look at their corresponding eigenvectors. So for lambda equals -3, what do I see? Let's make sure it's in the screen. Yep. So lambda equals -3, 4 minus a -3, that's 7, 1, 6, minus 4, 3, minus 7, 0, 0, minus 3, minus a -3. So that's -3 plus 3, that's 0. All right. So let's row reduce. So, dang it, this is not going to be all that fun. So if we're going to multiply, row number 1 by 7, by 4, row number 2 by 7. Let's see what we get with. 4 times 7 is 28, plus -28, that's 0. This is 716. 4 plus 7 and 3 is 21, so that's 25. This is 24 plus a -49. That's a -25, 0, 0, 0. So that's 716, 0, 1, 1, negative 1, 0, 0, 0. And that is 7. If I subtract 7 minus 0, 1 minus 0 is 0. 6 minus a negative 1 is 7. 0, 1, negative 1, 0, 0, 0. And that row reduces down to 1, 0, 1, 0, 1, negative 1, 0, 0, 0. So the null space of A minus lambda I looks like the vectors where x1 we have a pivot, x2 we have a pivot, x3 we have a free variable. So x3 is free to be anything, x2 must be equal to x3, oops, sorry. x2 is equal to x3, and x1 is equal to negative x3. So this is all scalar multiples of the vector negative 1, 1, 1. All right. So I'll write that in purple next to lambda equals negative 3. We negative 1, 1, and 1. All right, what about for lambda equals 2? Now, in the last case, where you had looked at the eigenvalue that had multiplicity 2 in the characteristic polynomial, it had 2 linearly independent eigenvectors associated with it. Let's see what happens in this case. If lambda is equal to 2, we get 4 minus 2. That's 2, 1, 6. Minus 4, minus 2, minus 7, 0, 0. Minus 3 minus 2 is minus 3 minus 2 is minus 5. Okay. So let's start row reducing. Okay, first off, before I waste some space, let's make this one 0, 0, 1. Scale row 3 by 5. Minus 4, minus 2, minus 7, 2, 1, and 6. That allows me to take row 2 and row 1 and subtract off 6 times row 3. So 2 minus 0 is 0, 1 minus 0 is 1, 6 minus 6 is 0. So essentially put the 0 right there. In the same way, I can multiply row 3 by 7 and combine with row 2, and minus 7 plus 7 is 0. So once I have a pivot right here, I could just put zeros everywhere above it. And what happens right here? I get 2, 1, 0, and I get 2, 1, 0, and 0, 0, 1 after scaling. So that makes this 2, 1, 0, 0, 0, 1, 0, 0, 0. Where I replace row 2 with all zeros, and then I flip-flop row 2 and row 3 because I want zeros all at the bottom, and thus I have 2 pivots. Okay, so I know that the null space of this matrix looks like all vectors where x3 must equal 0. Okay, x1 could be anything it pleases. And 2x1 plus x2 is going to equal 0, so x2 is equal to negative 1/2 x1, which makes it all scalar multiples of the vector 1, negative 1/2, and 0. And again, because I don't like dealing with fractions, okay, I'll multiply this by 2, so I get 2, negative 1, 0. All right, so if we look at these, it's not really going to show, so I can fold this over. In the 2 examples that we did, the first example we had 2 eigenvectors. This had multiplicity 1. multiplicity 1, and there was one eigenvector associated with it. Lambda equals 3 had multiplicity 2 in the characteristic polynomial. It had two linearly independent eigenvectors associated with it. In this case, lambda equals -3 had multiplicity 1, and there was 1. And in this case, lambda equals 2 had multiplicity 2, yet there was only one eigenvector associated with it. So let's see if we can make some conclusions, or at least come up with some speculation as to what is true about the correspondence between the multiplicity of an eigenvalue in the characteristic polynomial and the number of linearly independent eigenvectors associated with it. Here we go. This will do it. The algebraic multiplicity of an eigenvalue lambda I is the number of times the factor lambda minus lambda I appears in the characteristic polynomial. How many linearly independent eigenvectors can we find from all eigenvalues of a given matrix? Well, each eigenvalue will have at least one eigenvector associated with it. So in each of these cases, every time we had an eigenvalue, okay, we had at least one eigenvector in its null space, non-zero eigenvector in its null space. Whether or not a given eigenvector has associated with it more than just the one linearly independent eigenvector is related to the multiplicity of lambda. So here's the theorem. Let lambda I be an eigenvalue to the matrix A. If you look at S, which is the set of all vectors such that AV equals lambda I times V, this is a subspace of Rn. It's called the eigenspace that corresponds to that particular eigenvalue. The dimension of that space is at least 1 and is less than or equal to the multiplicity of the eigenvalue in the characteristic polynomial. So, in other words, to summarize right here, every time we had an eigenvalue, we had at least one linearly independent non-zero eigenvector. But for those that had multiplicity 2, we could have up to two linearly independent eigenvectors that formed a basis for the eigenspace. Okay, it doesn't mean you have to have two. You can have at most two. In this case, we had one. Okay. Now, if it were multiplicity 3, you could have 1, 2, or 3 linearly independent vectors that form a basis for the eigenspace. And so on and so on, 4, 5, 6. Eigenvectors that correspond to distinct eigenvalues are linearly independent. Okay, so that means this eigenvalue that corresponds to lambda equals -2 is going to be linearly independent of either of these. Okay. So these theorems explain why in each of the previous examples we were guaranteed at least two linearly independent eigenvectors, and at most 3. So this is a very important definition coming forward. Okay. An n by n matrix with fewer than n linearly independent eigenvectors is said to be defective. Okay. So in the first example that we looked at, okay, we had a complete set. We had 3 eigenvectors associated with all the eigenvalues that we found. In this case, we had 2 linearly independent eigenvectors associated with the eigenvalues that we had. This matrix is defective. We'd call it defective because it didn't have a complete set of eigenvectors. Okay, whereas a matrix with a complete set of eigenvectors is called diagonalizable or non-defective. This had 3 eigenvectors associated with this matrix, so it was diagonalizable or non-defective. This one had only 2, and so it was defective. It's a very important definition. All right. So we have two matrices here. Is the matrix defective or diagonalizable? Okay, we'll look at the one on the left. So first thing is we compute the characteristic polynomial. I've run out of scratch paper, so I got to make sure I use my space wisely. What's the characteristic polynomial here? It's the determinant of 5 minus lambda minus 1 minus lambda 5 negative 2. So 5 minus lambda times minus 1 minus lambda plus 10 is equal to 0. We get lambda squared minus 5 plus 10 equals 0. Minus 5 lambda plus lambda, so it's minus 4 lambda. Minus 4 lambda. So this is lambda squared minus 4 lambda plus 5 equals 0. Sorry, I'm just checking that because it's not factoring and I want to make sure that it's supposed to. 5 minus lambda minus 1 minus lambda minus negative 10, that's plus 10. Lambda squared minus 5 lambda plus 1 lambda, so that's minus 4 lambda minus 5. Okay. So we get lambda equals sorry about that. 4 plus or minus the square root of b squared, so that's 16, minus 4 times 1 times 5, all over 2 times 1. So it's 4 plus or minus 16 minus 20 over 2. So that's 4 plus or minus 2i over 2. And so lambda equals 2 plus or minus I. Okay, so I have two distinct eigenvalues, 2 plus I, and lambda equals 2 minus I. And so because I have two distinct eigenvalues, each of them will have an eigenvector associated with it. I actually don't even need to find that eigenvector because using my theorem that says distinct eigenvalues have linearly independent eigenvectors, I have two distinct linearly independent eigenvectors for a 2 by 2 matrix, so I have a complete set of eigenvectors. Therefore, this is going to be diagonalizable. And that's all I need to do. I don't need to actually find what these eigenvectors are. I know that these two eigenvalues will have one associated with it, and so that forms a complete set for this 2 by 2 matrix. Now let's look at the 3 by 3. Characteristic polynomial will expand across the top row. So the characteristic polynomial is going to be 4 minus lambda. Oh, sorry. Let's say what a minus lambda I is. It's 4 minus lambda, 0, 0. 2 minus lambda, negative 3. 0 minus 2, 1 minus lambda. So now we take the determinant of this. We get 4 minus lambda times the determinant of 2 minus lambda minus 2 minus 3, 1 minus lambda minus 0 times doesn't matter, plus 0 times doesn't matter. We're going to set that equal to 0. So this is 4 minus lambda times, in parentheses, 2 minus lambda times 1 minus lambda minus 6 equals 0. So it's 4 minus lambda times, let's see, lambda squared minus 2 lambda minus 1 lambda, so that's minus 3 lambda, plus 2 minus 6, that's minus 4. Okay, so lambda 4 minus lambda times lambda minus what? Minus 4, lambda plus 1, minus 4 plus lambda, there we go. So we have lambda equals 4 has multiplicity 2. Lambda equals negative 1 has multiplicity 1. Now, I know that lambda equals negative 1 is going to have an eigenvector associated with it by our theorem. So the question is, does lambda equals 4, does it have 2 linearly independent eigenvectors with it, or does it only have 1? If it has 2 linearly independent eigenvectors associated with it, then the matrix is going to be diagonalizable. And if it only has 1, it's going to be defective. So the nice thing about the work that I'm going to do here is I'm going to ignore this one because I know I'm going to have at least one, well, I'm going to have exactly one linearly independent eigenvector. The question is, for lambda equals 4, am I going to have an eigenspace with basis 2, with dimension 2 or dimension 1? So let's take a look. We'll look at 4 minus, a minus lambda I for lambda equals 4. So I'm going to write that down. I'm probably not on the screen, but that's fine. 4 minus 4 is 0, 0, 0. 0, 2 minus 4 is negative 2, negative 3. 0 minus 2, 1 minus 4 is negative 3. So that's a minus lambda I. So make that 0, 2, 3 up top. 0, 0, 0, 0, 0, 0. So I have one pivot right there. I have 2 free variables. So I know that x1 is free to be anything it pleases. x3 is free to be anything it pleases. This equation says 2x1, x2, plus x3 is 0. So I have x2 is equal to negative 1/2 times x3. So x2 is negative 1/2 times x3. So when you look at the null space, it's going to look like x1 times the vector 1, 0, 0, plus x3 times the vector what? 0, negative 1/2, 1. So 1, 0, 0 is an eigenvector. 0, multiply this by 2, negative 1, and 2 is also an eigenvector. So this 3 by 3 matrix is diagonalizable because it has a complete set of eigenvectors. This one, and whatever this one happens to be, but I don't need to find it because I know it exists by the theorem that was stated earlier in class. All right. Now, had this only had one linearly independent eigenvector associated with lambda equals 4, then I'd pair it with the one that's right here, and I would have 2 linearly independent eigenvectors, which is not enough for a 3 by 3 matrix, so we would have called that matrix defective. Okay, so that's section 7.2. The problems in this section kind of flow exactly like this, so, or more or less like this, I won't say exactly. So give it a try. If you have any questions, please feel free to stop by office hours.